So in this video, we're going to move on to doing static equilibrium analysis in three-dimensional problems. And all that really means is that the forces that are acting upon a body won't live in the same plane anymore. So the book kind of provides a motivating application for this. They show you an electromagnet. I almost said electromagnetic, but an electromagnet that is being used to kind of lift the load out of a scrap pile. And say we knew the weight of both the magnet along with the load, and we needed to basically determine if those chains are going to break that are connecting the actual electromagnetic to the hook. How would we do this sort of analysis? Well, it kind of feels like the problem that I motivated at the beginning of this lecture when we were interested in determining if the cables would break. So really the only different thing that's going on, we're going to approach it the same way physically. We're going to identify a portion of that body on which all of the forces of interest are acting, namely how the actual chains themselves pull on that body. And from that, we will solve and perform static equilibrium analysis and find what those forces are, and then basically see if they exceed a rated value. Unfortunately, in this text, we don't actually get to do that. But in real life, we would. But the question is, what's a little bit different about this problem than the one we looked at earlier? Well, all those forces don't live in a single plane. They're not coplanar. And that's not really going to matter. The analysis isn't going to be that much more complicated. It's just that we're going to have to enforce equilibrium in 3 dimensions, which means that not only do all of the forces acting on the body have to balance horizontally and vertically, but they also have to balance in that additional kind of 3-dimensional dimension, which we'll usually call Z. So really nothing's changing from a physical perspective. It's still that if a body is in equilibrium, which just remember means that it's not accelerating, that the resultant force is 0. However, if the resultant force can be expressed in 3 dimensions, we will have an additional kind of equation that will give us an additional degree of freedom to solve for an additional unknown. So the key point here is if you don't have a coplanar system of forces, if the forces aren't in 2 dimensions, but instead 3, you can in fact still do the problem, of course, and you can solve for an additional unknown. And I put the part about being well behaved in there. The book doesn't really get into this, but just do note that just because you have 3 equations in general doesn't mean that they're linearly independent necessarily. So you can't always solve for 3 unknowns with 3 equations. There are particular conditions on the relationships between the equations, but for us, we're just always going to assume that 3 equations means you can solve for 3 unknowns. So let's try to do a problem with this. Again, we have that familiar circular hook that showed up a little bit earlier today, and we're told that there's a 600 Newton load that's actually pulling it down, and we want to find the tensions developed in the chords AB, AC, and AD. So we kind of start with the same way we did the problem previously. We identify what portion of that body could we actually segment and draw a free body diagram of that would be acted upon by all of the forces of interest. And just like the prior problem, it just so happens that that kind of portion of the body is that little circular hook there in the middle. Now, what forces are acting upon it? Remember that when we kind of talked about in the last lecture, when you're drawing a free body diagram, you want to kind of go through your checklist and make sure you hit the weight of the object. In this case, we're just ignoring the weight of that little circle. Make sure that you actually describe any applied forces. In this case, it is that 600 Newton force that we were told is pulling it in the downward direction. And make sure that you include all of the reaction forces, which are serving to counterbalance the applied forces and the weight. And in this case, the reaction forces are nothing more than the actual forces that are exerted by the cables on that hook. So as we kind of described last time, the hook is going to be pulled by the cables towards their point of connection, just like the hook actually pulls the cables in the opposite direction. That's a Newton's third law thing. So if you do have any questions about why these forces that are exerted by the cables are kind of pointing away from the hook, just think about if that 600 Newton force is pulling that hook down, then naturally what is keeping it stationary is those cables are pulling it back up in the opposite direction. So hopefully that makes sense to you. But once we've actually drawn our free body diagram and identified the portion of the body that contains all 3 forces of interest, again, when we have our free body diagrams, we're trying to include as much detail possible about the magnitude and direction. That way we can attempt to solve for as many unknowns as we can, given the actual number of equations we have available, which in this case will be 3 because it's a 3-dimensional problem. Since these are all forces exerted by cables, there are cases where we know the magnitude, we just don't know the direction. So fortunately, since there are 3 cables, we have 3 unknowns, and this will turn out to be a statically determinate situation. So the question is, if I have forces that have a unknown magnitude, but they have a known direction, and it just so happens that in the case of a cable, that direction is aligned along the actual cable itself. The question is, what can we do about actually decomposing those forces into their I hat, J hat, and K hat components. That way we can actually enforce our three individual equilibrium equations. Well, this problem's a little bit interesting because we're given different piece of geometry in each case. So if you look at force B as denoted here by the free body diagram, you notice this lives purely in the XY plane. So it's only going to have an I hat and a J component. It's not going to have a K hat component. So how can I actually do the decomposition of this? Well, if you kind of break it down through a triangle rule and view it as a component that goes perfectly along the y-axis and perfectly along the x-axis, and make sure you're following your tip to tail rules of addition, notice that the component along the y-axis is going to be adjacent to this 30 degrees. So it's actually going to be related to the cosine of 30 degrees. So don't always try to, and you can't in this class, always rush to those formulas where you say, oh, x component is cosine, y component is sine. That assumes that you're given an angle that's measured in some conventional sense. Oftentimes that's not going to be what you're given. So just kind of look at your geometry and trace in, as I'm doing with my mouse, that decomposition of the force FB into a component along positive y and positive x. Notice that the positive y component is adjacent to that angle, so it's related to the cosine of that angle, and the x component is opposite of that angle, so it's related to the sine. So that's why I'm getting this decomposition, FB sine 30, FB cosine 30, and of course, since it's in the xy plane, there is no z component. I'm using kind of those triangular brackets instead of just writing the components times I hat, J hat, and K hat. So how would I actually go about doing the decomposition of C? Well, C is a very easy one because we see that given the coordinate dimension that we're using, the coordinate system that we're using here, it's directed purely along the x-axis in the negative direction. So we don't know its magnitude. However, we do know that it composes in 3 dimensions with an x component of minus that unknown magnitude FC, no y component, and no z component. So what about FD? How will we actually go about doing that decomposition? Well, this one's interesting because we're not given any kind of easy, it's not an easy switch situation like FC where it's purely along an axis. It's not a scenario like FB where it lies in a plane and we're given angular information. Instead, what we're given in this scenario is enough information to be able to write a unit vector along the line of action of that actual force. And the way that we can do that, if you go back, it's a little bit easier to see if you look at the original problem. If we know that this force acts along this cable, if we can find the actual coordinates of point D, and we know the coordinates of A again are just the origin, that's the way that we've made the choice, we can write a unit vector that is directed along that direction. So all that we have to do is find out the coordinates of point D. And again, sometimes these drawings are a little bit hard to see, but if you look, kind of go from D and drop down in the plane here, you notice they're saying that the projection of that point down into the XY plane is here. So in terms of the actual distance out in X, notice that it's 1 meter out in X. Notice that it's actually in the negative Y direction by 2 meters. And then you have to go up by 2 meters in Z. So that's how I'm getting this point. 1 unit in X, minus 2 in Y, and plus 2 in Z. So since, again, remember for your position vectors, always take the tip minus the tail, but if the tail is at the origin, it's just the tip. So that's why you have this, in this case, this really easy simplification to get the position vector from the origin to D. And any vector, any position vector, you can express it as a unit vector by simply dividing by its magnitude. And remember, the magnitude of a vector is always the square root of the sum of the squares of each of its components. So that's how I'm getting this. So even though we don't know the magnitude FD, we can decompose the vector corresponding to the force FD as that unknown magnitude times each of these X, Y, and Z components. So what do we do now? Well, fortunately, as I mentioned earlier, we got 3 unknown quantities, the magnitudes of each force, and in 3 dimensions, we will have 3 scalar equilibrium equations. So we're basically just going to take those 3 vectors, which we've written in terms of their X, Y, and Z components. We're going to take the common X components of each, add them, set it equal to 0. Take the common Y components of each, add them, and set them equal to 0. Don't forget that in addition to the forces that you have associated with the cables themselves, you also have that applied force, which of course, since it's directed in the minus Z direction, is just going to be written as 0, 0, minus 600. So if you just kind of take the common components here and write your equilibrium equations, you'll get a form of equations like this. You notice that they're a little bit actually coupled in this case, and not, what usually happens with the textbook, I think it's where it's a kind of an older textbook, they try to make the problems in such a manner that you can solve them easily through substitution. That way you don't have to use any kind of linear algebra techniques. So if you look at the set of equations, the first equation involves 3 variables, the second involves 2, and the third involves only 1. So you can easily solve the equilibrium in Z for FD Once you have that, you can solve equilibrium in Y for FB. Once you have that, you can plug both in and get the remaining unknown, which is FC. However, feel free to just use a calculator as well. You don't have to incrementally solve by substitution like that. So key point of that is just to know that you are, and we're going to do some more examples of this next week when we get the homework up, but know that you can do static equilibrium of particles in 3 dimensions. Nothing really changes. You just have an additional equation, which allows you to solve for an additional unknown. And just like in Chapter 2, those problems get complicated sometimes, not because they're really any tougher, but because it's hard to read the geometry out of the diagrams that the book gives you. So I hope you had a good week, and I will see you all next week, where we'll start right away with looking at some actual example homework problems from Chapter 3. And I'll put your Chapter 3 homework up in My Engineering. And then don't forget that your Chapter 2 homework is due on Sunday at midnight. That is on 9/11. So I will talk to you all soon.